This question then is looking at comparing Kekulé's model of benzene against the updated delocalized model of benzene. Okay, so you've got a little bit of history in the question here. It's telling you when Kekulé devised the model that he is so famous for. It says experimental evidence has led to the development of an updated model, which is this one now, and both models are shown. Explain the experimental evidence that led to the development of the updated model from the Kekulé model of benzene, and describe the bonding in the updated model of benzene. There's 2 parts to this question. There's 4 marks available for it, and this is very common. This comparison of the 2 models, the idea of trying to describe the structure and the bonding present in this molecule here, and outlining Kekulé, the evidence against Kekulé's model is very, very common indeed. So it's worth trying to learn or get to grips with a pretty standard answer for these sorts of questions. All right, so let's start off with our 3 pieces of evidence that we've learnt about, which discredit Kekulé's model of benzene structure. So what do we say? Benzene, first of all, does not decolorize bromine water. What does this mean then in terms of the reactions? Well, we know that alkenes can decolorize bromine water. So if Kekulé's model was correct, the fact that we've got 3 double bonds there would suggest that this version of benzene would readily decolorize benzene. Therefore, it would undergo electrophilic addition reactions just like alkenes. So the fact that benzene does not decolorize bromine water means it does not undergo electrophilic addition reactions. Which you would expect it to do if Kekulé's structure was correct. Okay. The second piece of evidence was bond lengths. All the bonds are the same length. Okay. If Kekulé was correct, the double bonds would be shorter than the single bonds, and therefore the actual structure of benzene wouldn't be a perfect hexagon. It would be slightly skewed. It would be slightly misshapen. But X-ray diffraction showed that the structure of benzene was a perfect hexagon and showed that all the bonds are the same length. Okay, so let's just clarify that point. All the bonds are the same length, which would not be the case in Kekulé structure, in Kekulé benzene, as double bonds would be shorter than single bonds. The third piece of evidence, okay, the third piece of evidence refers to the enthalpies of hydrogenation. So we can say that the enthalpy change of hydrogenation is less exothermic than expected. Which means benzene is more stable. All right, so that's 3 of our 4 marks there. Describe the bonding of the updated model in benzene. So anything like when you see this to do with describing the model of benzene, you can describe this by a diagram, by a labeled diagram. We haven't got to do it in words. So anything to do with benzene structure, I would simply draw my hexagon with the p orbitals your dumbbell shape, label them. Okay, make sure you label all your diagrams, producing a pi bond or a pi cloud as the p orbitals overlap. Okay, and that would be a perfectly suitable explanation, description of the bonding in benzene. Without the labels, it's meaningless. So make sure any diagrams you label, any diagrams you draw are clearly labelled. You should also state on this question that the electrons in the p orbitals here, in the pi bonds here, are delocalized. It's always wise just to refer to that, as well as stating about the orbital overlap. So electrons are delocalized.